Oh, hello. Monaco here.
Milk's behind the camera.
This is your last video pre-lab of the year.
Woo!
We're going to model some radioactive decay, and hopefully this lab experience will be very familiar to you with a slight twist. Okay. You have hopefully studied radioactive decay when you did earth science, and so you understand how radioactive elements turn into other elements over time. For this background, I want you to find some information from the net about radioactive half-life, radioactive decay. Show us some notes, bullets about what you have learned solo. This is kind of the fruition of everything that we've done. Purpose, I gave you 3 bullets. We want you to model radioactive decay of atoms using the candium. That's a radioisotope. Haha, it's a joke. We're going to graph the parent and daughter nuclei that remain after each shake of atoms. And then we're going to use these graphs to determine the radioactive half-life of that candium isotope if we pretend each shake equals 10 years of real time. Okay? So in your procedure, I'm going to model that for you. So I want you to record in your own words, step by step, what I am going to show you. It's very simple, straightforward. So come on over to the lab space. The first thing you need to do is get approximately 50 Skittles or M&Ms from your teacher, me or Mr. Milks.
Yep, you get a choice.
And the cup that we give you at first, sometimes there's defects. As you're counting your original count, clean out the defects. You have permission to eat the ones
What is a defect, Mr. Monaco?
Defect is one that is cracked, squished, misshapen. You need the classic Skittles shape with the S or an M on it.
I see it now.
You see the S? You need one side
I now see the S.
to have nothing on it, and the other side to have a mark, an S.
Okay.
Or if you're working M&Ms,
And the M.
the M.
Gotcha.
Because that mark is going to tell you when one of your radioactive candium isotopes has decayed from the parent radioactive element to the daughter element.
All right, I got another question.
Yeah.
So I went to Milks in Monaco. I got my candy. I chose. I got them. I count them, and now I can just eat them, right?
No, you need to do the lab experience with these, okay? So in our procedure, the first thing you got to do is get your candium, make sure they're all ready to go. I see one right here, for example, that I can't really tell that's got an S on it or not, okay? And the other side is blank. So that one, I'm going to get rid of because that's not going to help me out in this lab, okay? So I have approximately 50. You might have 55, you might have 60, you might have 45. It's okay. You need to know how many you start out with.
Yes.
The second thing you're going to do is you're going to go to your data charts. Okay? And you start out at 0 shakes, and you have undecayed candium atoms. This is how many you start with. So
That could be your 45, your 50, your 48, whatever that is.
I know I have 49. I better see different numbers on your papers. Now, you also have 0 decayed ones.
Got you.
Okay. Next thing you got to know is that a decayed candium is one that has shown an S.
Yeah, the letter up.
If the letter is up, you know it's changed from the
The
radioactive.
letter is up after I shake them now.
After I
So
shake.
let's do that.
So, letter up equals decayed. Letter down equals still radioactive. So, I'm going to show you what a first shake is going to be like. You take your candium and you give it a good shake, 10, 15 seconds. You're juggling. Pour them out in a nice safe spot. Now you can see some of them flipped with the S up,
Got you.
others did not. So now you have to sort your elements. Sort and count. I'm going to sort and count. So remember, letter up means it's turned into a different element. So we're going to put all the letter ups over here, and the letter down we're going to keep over here. You're going to sort them through. Okay? Letter up, letter up, letter up, letter up. I am separating the still radioactive ones from the ones, oops, I put these in the wrong pile, from the ones that have gone through a radioactive decay. Oops, if you drop them and hit the floor, oops, it is what it is. Okay, so it looks like I've got a pile of elements that are still radioactive and ones that have decayed. Oh, missed one. Now I count and I record in my chart. After one shake, how many undecayed do I have?
Or those are the decades, right?
19. I've got 19 letter ups decayed. So number of decayed atoms, 19. Undecayed would be the difference. So that's actually 30, I see. I can do some maths. So I take my undecayed atoms,
Shake again.
and I put them back in the beaker and go through another half-life. Same exact way. And I sort and separate and count again.
Now, how long do we keep shaking these?
Until you have like 1 or 2 left.
Okay.
Or you get through 7 shakes.
Okay.
However many left over after 7 is how many you've got.
Now, you can't eat them yet.
Nope, don't eat them yet. So I'm going to separate again. As you can see, I'm changing here, and I count. The number of undecayed is going to go down. The number of decayed is going to go up. So once you finish a full data set for trial 1, you need to do it again.
You need to start with all of them all over again.
All of them back.
That's why
into
you
the
can't
bucket.
eat any yet.
Can't eat them yet. You will get to eat them when you're done and your data has been checked and validated.
And this is why we're doing it on the paper towel, guys.
Because you are going to eat these.
Well, if you want.
If you want. If you don't want to eat them, then you don't give them someone else. So on to trial 2. You again start out 0 shakes, 49, 0, because I know that I start with the same one. I haven't eaten any or lost any in the process. Go through the process again.
Okay, good.
Remember, letter up means it's changed, letter down, still radioactive.
Can I put that? I've been resisting showing them this.
Okay, but I would like better words than mine. Do that 3 times, and then we need to average the results.
Ooh, average. Add them up, divide by 3.
Because the number of trials, we had 3 trials. So for real-time past, we're also going to change the number of shakes to real times past. So remember, that was 10 years of time for each shake. So instead of 1, 2, 3, 4, 5, 6, 7, we're going to go 10, 20, da, 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 da.
Years.
Years, Y's, years. Now the undecayed candium atoms, this is the average of your 3 trials. This is the average of your 3 trials. So you'll take all your number of undecayeds from 0 shakes, average the 3 numbers together, and write it down. Then what do we do, mister?
We're going to, how about we graph?
Graph it. You're going to graph your average results. So quickly, there's instructions for how to set up your graph. We want to do a double line graph. Okay, so you're going to graph both the decaying atoms.
Okay, so one's going to go down.
One's going to go down, and one as the undecayed one's going
Different
up.
color, pen or pencil, something.
Right. I'm choosing 2 different colors. I'm going to use orange for the radioactive, green for the radioactive ones, and orange for the daughters. Okay. You're going to see where this graph crosses at some point. Once you have your axes set up, you're going to see a point where it crosses, and this is the time where that is the number of half-lives. So where the 2 graphs cross is the exact time period of how long it takes
For
to hit
one
one half-life. It's not going to be 10 years, it's not going to be 20 years, it's not going to be 30. It's going to be somewhere in between because we're averaging our results.
Beautiful.
So you're going to look at table N after you've plotted your results and propose a nuclide that candium might be based upon the given half-life. So you're going to figure out how long that half-life is. Okay? The time is not on this axis. I made a mistake. Time's going to be down here. You're going to know how long that half-life is. You're going to compare it to table N.
Who's close?
See which one's closest. Propose an identity for your theoretical element. And then you're going to go on to your CEI. Restate the purpose, the claim. I believe the half-life of the candium isotope is, how long do you think it is from your graph? Data and evidence. My data shows that to tell me exactly what's going on, when I went through radioactive decays, the daughters went down, or then the parents went up, whatever it might have had happened. And so in your interpretation, you're going to explain how you use your graph to determine the half-life of the isotope. So by graphing the average and doing a double line graph, you could see where they crossed and determined how long that took on the time axes. So, and that's really it. Just want to let you know though, if you like learning about radioactive decay, go ahead, go find out more information out there. Use those keywords, radioactive half-life, decay, parent nucleus, daughter nucleus, all that stuff, because the sky's the limit, okay? Thanks for watching.